Hello! Today we're doing 1.4b, continuity and one-sided limits. So yesterday we talked about one-sided limits coming from one side or the other. Today we're going to talk about some more properties of continuity. So this says if b is a real number and f and g are continuous at c, then the functions listed below are also continuous at c. So if we have any two functions that are continuous, if we multiply those two functions, we also get a continuous function. Or if we multiply the function by some variable, some value for b that is actually scalars like a number, then it would still be continuous. If we multiply the two functions together, it's still continuous. If we add or subtract the two functions together, the function would still be continuous. And if we divide them, as long as the denominator does not equal 0 at that point, it would also be continuous. So that's kind of helpful to know that if we combine some of these things. So this says, are the following functions continuous? This would be yes, because x and sine x are both continuous. So because we added the two together, we know that it's still continuous. All right, tangent x. Is tangent x continuous? Well, and it says at every point in its domain. So tangent x would only be continuous within its domain. But with the 3, it still would be continuous within that domain. So 3 tangent x is continuous on its domain only. So on the values that tangent x is continuous, 3 tangent x is continuous as well. Not continuous at every point, right? Because tangent has some asymptotes there. X squared plus 1 over cosine of x. So this would be continuous, except where? Where cosine x equals 0. Which, let's think about that. Sine comma cosine, cosine comma sine. Our cosine would be 0 at pi over 2 and at 3 pi over 2. And then, of course, the ends as it goes around the circle. So it would not be continuous at pi over 2 or 3 pi over 2. Okay, next, describe the intervals on which the function is continuous. So the tangent function is undefined at pi over 2 because, look, if we're looking at this, tangent is sine over cosine. That's where we divide by 0. So tangent x cannot equal pi over 2 or 3 pi over 2. So that one's not okay. But basically, pi over 2 is just a circle around pi, right? If we go pi around pi is half of a circle, then we would get to 3 pi over 2. If we go another pi, we get there. So pi over 2 plus pi n. This means that we're starting at pi over 2, and we're going halfway around, halfway around, halfway around, halfway around, forever, as many times as we go around the circle. So that would be where it is undefined. At all other points, it's continuous. So it's continuous everywhere except where x equals that. Okay, let's look at our next one. This is a piecewise function. G of x is sine of x, sine of 1 over x where x does not equal 0, and 0 where x equals 0. So because 1 over x, this is continuous, except at x equals 0, and the sine function is continuous everywhere. Therefore, this would be continuous except at x equals 0. Because that's where this function is not continuous. But look, we have the point 0 here. At x equals 0, the limit of g of x does not exist. But then we have this point here for 0 when x equals 0. But that would make g of x continuous for negative infinity to 0 and 0 to infinity. All right, last function. This one's similar to part B, except that it's a little bit different. because we have this x out front here. And so if we were like to use our squeeze theorem here, we would know that what's actually happening is this would be discontinuous at 0. However, the negative absolute value of x is between, this is our squeeze theorem that we talked about the other day. If we have this in between, we know that the limit as x goes to 0 of h of x is 0. So therefore, it's continuous everywhere. Continuous for all real numbers. Okay, intermediate value theorem. This is huge, guys. This is going to be used, probably one of the theorems you're going to use the most in calculus, and you're going to need it a ton on your AP test. So this says if f is continuous, so we know what continuity means. It means that our limits agree. On the closed interval, a, b, and also continuous, our limits agree and the point exists there. So if the function is continuous on the closed interval a, b, where they do not equal each other, they're different points. So we're saying we have some function here, and it's continuous. It doesn't stop anywhere. K is any number, so I'm just going to say this is a, and I'm going to make this go up a little bit higher just to make it work for our point. This is b. I guess this would be a and b, and this would be f of a and f of b. As long as these don't equal each other, k is any number between f of a and f of b. Like say something here, call that k. Then there's at least one number in C such that f of c equals k. So basically all this is saying is that if we have 2 points on a line and there's a point in the middle of them, if our function is continuous, it's going to have to go through that point at some point. So basically the middle value will be included in your function at some point between those two, as long as these aren't the same. Why not if they're the same? Because if they were the same, then it could just be just a line. So they have to be different, and then it has to be a point between them. So this is where the intermediate value theorem is super helpful. And feel free, anytime that you use that as a proof, you can write IVT as intermediate value theorem, and that would be widely recognized. Use the intermediate value theorem to show that the polynomial function has a 0 in the interval 0 to 1. Okay, so is it continuous here? This is a continuous function. Yep. So this would be continuous. And let's find out what f of 0 is and what f of 1 is. Let's plug those in. If we plug in 0, we're going to get negative 1. If we plug in 1, we would get 1 cubed plus 2 times 1 minus 1, which gives us 2. So we have these points, negative 1 to 2. And it wants us to use that this has a 0 between 0 and 1. So we know f of 0, which was negative 1, is less than 0. And f of 1, which was 2, is greater than 0. So that means the intermediate value theorem, by the intermediate value theorem, there must be some c, and that just means some value, in 0 to 1, such that f of c equals 0. So it's saying, like, if we have this point 0, negative 1, and then we have the point 1, 2, we have to cross through 0 at some point. That's all that we said. So here we're just, to write out like the formal proof, we're saying as long as our f of 0 is less than 0, our f of 1 is greater than 0, so there has to be a middle point at 0 at some point.